Okay. And this is exciting because, you can see today we've got the fundamental theorem of calculus on tap. And so that's exciting because we're in calculus. That seems like it should be pretty important. And the whole point of that is actually getting the area under a curve. That's kind of where we're at. I guess maybe before we dive into the questions about anything, how's homework going? Let's see, I remember correctly. We had related rates and L'Hopital's rule. Looked like almost everyone did pretty well on that. Some people need some help, which is fine. But we'll have a quiz on that today. So there are thoughts about anything before we get started? Sure, I got my chat open. Okay. Okay, if not, sorry, let me keep going. Okay, let's remember where we're at here. So let me remind you of the notation here. We're talking about antiderivatives. And antiderivatives, we're thinking about this little f of x. And then we take the antiderivative and we find the big F of x, right? And we have all these rules about how to do that. All these rules that we were looking at last time, right? All these antiderivative rules. And in each one of these cases, again, here's that notation, right? We think about taking the antiderivative as doing the opposite of a derivative, right? The anti of the derivative. And so the rules we saw last time were some of the quote unquote kind of easier rules, like doing the anti-power rule, for example. We did that a couple times. That one comes up a lot. And we moved into a couple of the more, I don't know if they're harder rules, but the not anti-power rules, right? Like the sine and cosine rule. And the reason I want to just remind you of that is because in each one of these cases, we had something we were integrating, which we're thinking about as little f. And then when you actually do the integration, which is antiderivative, we get the capital F of x, okay? And that's just important because this next page uses that notation. So I just want to be clear about what we're talking about when we see that on this next page, right? So, so the fundamental theorem of calculus, again, it sounds like it's important because we're in calculus and this is a fundamental theorem for it. And so one thing we're trying to learn here is what it says right here, which is talking about how the antiderivative can be thought of as a definite integral. So this is known as a definite integral, which we'll talk about in just a minute here, where now we have the squiggly mark, right, which we call the integrand, but notice how there are bounds on it, right? And this first one says a to x. And what that means is sort of explained more carefully down here, where if we want to actually do this antiderivative, which I've got circled in green now, if we want to do the antiderivative between 2 points, A and B in this case, I'm sorry, we do the integral between A and B, it involves taking the antiderivative and plugging in those bounds, right? So notice how we've got capital F, and inside capital F, B and A are being plugged in, right? See that? So just kind of harping on the notation a little bit. And this is kind of the big important takeaway, I would say, of this page, the thing I'm going to box in red here. Maybe I'll throw a star on it. This is how we're actually finding the area between the function and the x-axis. That's what we've been sort of building up to over the last week or so. We started by putting rectangles. What's the word? Rectangle. We started putting rectangles under there to approximate it, right? That's where we were looking at early on here, where we had some error involved in doing that. And now in this particular page, in this section, we're going to get the exact value, right? We're getting this kind of idea now. And you can see we started with that notation last time. So that's where we're at here. Let's draw a quick picture on this page, wherever we are. Here we go. To actually figure out what this looks like, right? So, so notation, there's another notation thing here. This notation right here means I'm about to plug things into the function. And so notice how there's an x on the left-hand side, but then on the right, there's a b and an a. And so when you do the antiderivative, when we do this integral, like integral of a to b of f of x dx, we get this intermediate step where this is the antiderivative. And you'll see me do that. And so I just wanted to kind of make that clear. It's like we're going to do this integral, you do this intermediate step where you find the antiderivative, and then you write down what you get when you plug the numbers in. And sort of the takeaway, the thing that we're trying to do here, the whole point of this, is we're trying to estimate the area between the function and the x-axis, right? And so let's say this is our function. And let's say A and B are, let me get another color here. Let's say this is A and maybe B is over here somewhere. If we were going to integrate this function from A to B, take a second and think about what should I shade in? If I was going to integrate from A to B this function, what part of this graph should we shade in? Just kind of think about it yourself. Maybe you could sketch it on your paper font. At least activate your brain a little bit and think, what should I be shading in, right? We're getting, let me be more clear. Let me zoom in here. This is going to tell us the area between the function and the x-axis. Right, and I've got my A and my B labeled there. And so the thing I'm trying to get you to think about is some of the functions above the x-axis and some of it's below the x-axis, right? And so if we were going to integrate this between A and B, what area would we actually be finding, right? That's sort of what I'm thinking about. So again, between the function and the x-axis, right? So part of it's going to be this piece, right? But then when the function goes below the x-axis, you're measuring this part of it, right? And then when it goes above the x-axis again, all of a sudden you're doing the top part again. So starting to kind of visualize what we're doing here. And we're going to draw a bunch of similar kind of pictures today to try to be clear about what we're doing. Questions about what I'm trying to say there? It's a shaded area so that we don't get any, sometimes people, the reason I like to do this, sometimes people think we're estimating this area in the middle there. That's not part of this calculation because that's not between the function and the x-axis. All right, you with me? Notation? Thoughts about that at all? What we're about to do? I'm going to be more clear about that, just in case. So what I'm trying to say here, it's the shaded area, the shaded region, regions. Okay, we're okay so far, right? All right, anyone online need to chime in here? Just make sure my speakers are working. Okay. Okay, the next part before we actually do it is what about the plus C? You can see it says right here, what about the plus C? And what I mean by that is in the last class, we spent a bunch of time talking about how, wherever it is, when you integrate something, you should always write down plus C to represent constants that might be there, right? Like these right here. Because when you take a derivative, they go away. And so when you integrate, you put a plus C to say, okay, there might have been a constant here. And so notice how in this notation, there's no plus C right here. Right? Like some people think, well, you just told me when we integrate, we need to put a plus C right there. Why isn't there a plus C? And so I just like to talk about where did the plus C go? And so let's just sort of talk about that real quick. Does anyone have an idea about that? Why don't we put a plus C, or what would happen if we did put a plus C? Right, if each one of these things right here got a plus C with them, what might happen? That's sort of what we're thinking about. So let me write down the question and maybe someone has an answer. The question is, why not, when you integrate this thing, do we get this? Right, like why is that thing up there? Where did the plus C go? Any ideas about that? Question mark. Anything? Any ideas? So that's the question, right? People sort of think like, well, the plus C would be there And if it's not there, does it change? And so I guess my argument would be it wouldn't actually change the value if we include it. Yeah, that's a good thought. Why? And people see what I'm saying there, right? If we put a plus C right here, and then we subtract, and we have a plus C right here, they just cancel each other, right? And so, and that's what I'm about to show you. So the idea is they just cancel anyway. And so, yeah, we could put a plus C in there, but they're just going to cancel out. And so we just don't. And so notice, if we were to do a plus C, so let's go ahead and do it. Right, so this is, I've done the integration, I've got the antiderivative, I'm about to plug the points in. Let me make that a little bit easier to look at. The straight line with the AB means I'm about to plug these points in. If we did that, the C's are just going to cancel. Right, this C is just going to cancel out without C because you're subtracting, and you just get the thing that it says up at the top there anyway. And so the takeaway here is we just don't need the plus C with integrals that have bounds, which are known as definite integrals. But we haven't defined that yet, so I'm just going to say with integrals that have bounds. So when you have numbers on them, I'll just put it in parentheses. These are known as definite integrals. All right, question about what I'm trying to say there, or sort of the setup. We'll obviously do a couple examples here that I hope kind of illustrate the idea. Yeah, that's right. Anything there? Actually, was there something else I was going to say about this? I thought I used to have something else on this page. Maybe I took it out. I'm sorry. All right, there aren't questions. Let's do a couple. I'll do a couple, you do a couple. Feel good about this. So the first couple things I like to emphasize is the difference between positive area and negative area. And so if we're above the x-axis, we get positive area, and if we're below the x-axis, we get negative area. So kind of like looking back at this picture, the area here is going to be less than 0, and the area here is going to be bigger than 0 because one's above, one's below. And so we're just going to look at a couple of examples that kind of emphasize this idea in these two pictures, right? Let's actually just go ahead and draw the pictures. So in this first one, e to the x, we're just integrating e to the x from -1 to 1. I hope we all kind of know what e to the x looks like. E to the x just does this kind of thing, right? And so we're about to calculate this area. And it's above the x-axis. All of it's above the x-axis, and so it should be a positive number is what I'm trying to show you here. Let me just draw the other picture while we're at it, while we're in a drawing mood. The other picture, t squared minus 4t, I also graphed this one ahead of time, and it looks like this. I remind myself it's like an x squared thing, right? Yeah, it looks like this. Right, and you can see the numbers that are on the bounds here are 0 to 2. And so 0 is right where it starts to be negative, and 2 is like right in the middle. And so we're going to end up finding this area. And just visually, it's all below the x-axis. And so if it's all below, then it's going to end up being negative. All right, let me just sort of pause there and let everyone finish getting those graphs written down. Questions, though? All Everyone online doing okay? Who knows? Bunch of black boxes. Probably just sleeping. I don't know. Oh, I do have. Oh, all good here. Roger that. Thank you. Yeah, so the question online was, why did I only shade half that graph? Because this 0 to 2 is telling me to go from 0 to 2. Yeah, so that, thank you for pointing it out. Just like this one minus 1 to 1 is because the integrand is telling you where we're evaluating it, right? Yeah, good thoughts there. Sebastian's not sleeping. I knew he wasn't sleeping. Other thoughts about that? Those are good things. I'm sorry?
In the top.
One more time, Janetta.
I really don't understand why it can't be in the top.
Why it can't be in the top? Why what can't be in the top?
Why the area?
So these numbers, I'm not sure exactly what you mean, but these numbers tell you the bounds that we're using.
Okay.
So minus 1 to 1, for example. That's why the graph over here is going from minus 1 to 1. On the other one, maybe you're talking about the second one, right? So this one's going from 0 to 2.
Yeah.
And so that's why on this graph, it just happens to be this area that's below the x-axis because it starts at 0 and ends at 2. Oops. And so it's this part right here. Is that what you were asking? I don't know.
Yeah.
Okay. So yeah, it could be this area if we went out like, I think this is probably 4. So if we went like from 0, if the integral was from 0 to 6 or something, then we'd start doing the top part.
Okay.
He's asking about like what you mentioned earlier about the area at the top. Are we not using that?
Sorry, just laughing at this comment in the chat. I never sleep. Also, what's it called at the top? So let me first talk about Janetta. So was your question maybe, Janetta, why are we not doing this area? Yeah. And so that's because the definition we're doing here, it's the area that's between the function and the x-axis. And so that's sort of what I was trying to originally convey in this first graph, right? Like we don't have this part right here because the graph is down here and the x-axis is there. And so we're doing what's between the two of them. And so if the graph goes below, it ends up being this part, right? And then when it's above, because the x-axis, maybe that's what's not clear, I don't know. The x-axis is the part going right through the middle, right? So that's why it's either above or below.
Okay, that makes a lot more sense.
And then why is it, what's it called? Is the top one always the one that's furthest to the right? Yeah, so I think what you're trying to say here is when you write down this integral, a comma b, a is always a smaller number. Is that sort of what you're saying? I should have turned off my highlighter there, sorry. So that's why when we look at these integrals, the top one's going to be the bigger number and the bottom one's a smaller number. Right, so minus 1 to 1, 0 to 2. Smaller number to bigger number. All right, these are great questions. And man, these people online are making you people in person look just, you guys are sleeping. No, I'm just kidding. Other questions? All I had to do was tell them that I thought they were sleeping and then I jumped on. You don't have to wait for me to tell you you're sleeping to ask questions. Big Z's in class. I know what it's like to jump on a Zoom call and turn your camera off, believe me. Okay. The thing is determining when it's appropriate to do that. It's something I need to work with some of my classes about. Okay, so let's do this. Let's actually do it. We know the antiderivatives, but I'll just remind you, right? We're going to use e to the x for this one. E to the x just stays the same. I'll just kind of remind you of that real quick. But right, when we integrate e to the x, it just stays the same. So that's a nice, easy one. And so starting off easy, right? When you do this integral, it just stays the same. And then we're going to plug in the points. So a lot of this one is like the notation, right? I've got e to the x inside the squigglies, and then I've done the integration, even though it looks the same. This is my little f, this is now my capital F. And now I'm about to plug the points in. That's what the straight line -1 to 1 means. It means you already did the integral, now plug the points in. And so when we plug the points in, we just get e to the 1 minus e to the -1. Right, this is my f of b minus f of a. So look okay. And e is a number. Don't ever forget that, right? E is a number, so we can use our calculator to get a number out of this. Excuse me, this is like e is about 2.72, right? So it's like 2.71 or 2, I can't remember. 2.72 minus 1 over 2.72 or something. If you had a calculator, we can figure that out. I did ahead of time, and this ends up being about 2.3435. But the thing, so first of all, one thing, this is an integral. This is what's called a definite integral. We just found that area that's highlighted in blue. And the thing I'm trying to point out is that notice that 2.35 is a positive number because the area is above the x-axis. Nice, kind of easy one to get us started here, but hopefully that all makes sense. What do you think?
It makes sense. Yeah, it makes sense.
I'm sorry, say that one
Or
thing.
when you say in English words, I think it's like the area between the x-axis and the integral bound.
Yeah, the area bounded between the function and the x-axis is 2.35. And remember, we'll see some applications of this in a second, but it adds up the total amounts, right? This is some function that doesn't have meaning right now, but if this was like the number of births that were taking place, we could say like, oh, well, between this time period, 2.3 births happened, or two new infections took place during this time, or something like that is what we're eventually gunning for. I think I've got some applications a little bit later. Other thoughts? I heard someone online said they loved it. Any other comments or questions? All right, let's look at this negative one then. So before we do anything, right, the graph that we're looking at is below the x-axis, or at least the piece that we're looking at is below the x-axis. Should be a negative answer. Right? Conceptually should be negative. And this is just the anti-power rule that I hope we kind of feel okay about right now, but we're going to add 1 to the power and divide by it. And so let's do that. So this is my, just to be clear, this is the graph t squared minus 4t, right? Oops. And we are going to integrate this from 0 to 2. What I like to call the anti-power rule. Add 1 to the power, divide by it. Add 1 to the power, divide by it. And then we're going to plug in 0 to 2. Just note this one more time. Started with little f, end up with big F. Is that okay? Questions about that anti-power rule at all? And now we have 2 terms, right? So plugging things in is a little more challenging because we have 2 things to plug it into. And so let's just be a little bit careful about what that looks like. So that looks like, I'm going to do the details on it. It looks like this, right? That's f of 2, so that should be a 2 in there, not a 3. And then we plug in a 0. And the 0 one just goes away. Like I certainly don't need to see that if you can realize it goes away. Just trying to be very clear about how you plug these numbers in and get the answer, right? So the answer is just going to be what's in the second, or the one on the left, because the other one just becomes 0. Okay. So we just get, I'm just going to be super clear in case anyone's confused. We just get something from the first one, which ends up being minus 5.3. And it's negative because it's below the x-axis. All right, hopefully that makes some sense. What do you think? Okay, cool. Is that okay? Thoughts? One's positive, one's negative. Just do a couple more kind of easy examples to ease us into it. I would like you to do these two actually, but we can at least set it up and draw the graphs together. So one thing is saying the next idea is like, well, let's just draw the pictures first. Both these next examples have a graph where some of it's above the x-axis and some of it's below. Right, and so what we're going to see is there'll be some sort of canceling effect. That's what sine looks like. And then x cubed does this, right? But notice the bounds. 0 to 2 pi on the first one. Okay, well that starts here and goes all the way to the end. What's that interval going to end up being? If the second one goes from -1 to 4. -1 might be right here, but then 4 goes quite a bit further to the right, right? So what are those going to happen when we do that integration, right? Thinking that through. So I'm going to let you work on this, but I'll give you a little hint about the sine one, because let me give you a big hint. At the end of class, there's going to be a quiz that's going to involve plugging things into sines and cosines. Is that right, actually? What is on that quiz? It involves plugging things into sines or cosines. So I'm going to write this down to help you. Sine of 0 is the same thing as sine of 2 pi, which is 0. And for cosine, those equal 1. And so I would encourage you to write those down now and then use them on the quiz. I'm not going to say that again on the quiz. We're going to need that for the quiz. But you're also going to need it here, because sine, when you integrate it, becomes cosine, and then you're going to plug in 0 and 2 pi. And so you're going to need the sine one here, and I think you're going to need the cosine one on the quiz. Okay. Because I just happen to know, you mean like, how did I know that this was 2 pi over there? I just know what sine looks like as a graph. In the middle is pi. And so that has to do with like the unit circle. Unit circle starts at there, and then when you go all the way around, you're at 2 pi. So it's like a trig thing that I would love to talk to you about if you want a little bit of a refresher, but that's sort of where it comes from. Other thoughts? Or I just let you work on that for a minute? All right, try this too. So sine becomes minus cosine, right? Plug in the numbers. X cubed is the anti-power rule. And let's think about what we get. And does it match up with your picture, right? Does your picture show you the right thing? I'm gonna shade in my picture a little bit. Maybe before anyone finishes that first, and maybe you already finished it. What do we know we're gonna get on that first one before we do anything? Just looking at the picture. Yeah, it looks like it should be 0. Why do you think that?
-1 and +1.
Yeah, exactly. Good, everyone. It's like the same shape above the x-axis as it is below the x-axis. We're doing the same area both. I drew a bad picture, but you can imagine they're supposed to be the same, right? So they're just like going to cancel each other out. And then on the second one, using that same logic, there's more above than there is below, and so that's going to end up making it positive, right? All right. But anyway, let you work on that one more, just a minute longer. I'll kind of slowly start writing things down here. So sine turns into minus cosine. Ooh, be careful with that negative, right? This is where you catch mistakes. I can already see myself making a mistake here. Anyway, sorry, I don't mean to disrupt you. Just be careful about that negative. All right, so sine becomes minus cosine, and I was, warning you about that negative because when you do minus a minus, it becomes a plus, right? And so you get this double and negative situation in the middle there. And so we said cosine of 2 pi is 1, so you have minus 1 minus minus 1. That's why they end up canceling to 0. And that's one of the reasons I wanted to draw the picture, because if you kind of have an idea what the picture is, you can catch a mistake if you forgot about that negative sign. Like if you didn't have that negative sign, you'd get an answer of -2. But if you look at the picture, you're like, wait, wasn't that supposed to be 0 based on what I know? And you can just catch a mistake that way. Thoughts about that one? Is that okay? All right, and so it canceled out. And so I guess one thing I was trying to point out there was area above the x-axis canceled with the area below. And the opposite thing's going to happen, not the opposite thing, a different thing's going to happen here. So x cubed, add 1 to the power, divide by it, and we get x to the 4th over 4. Remember, you can always double check that, right? If you did the power rule on this thing, bring down the 4, it's going to cancel the denominator, subtract 1 off the power, we get back to the original. So you can always check your work there. At least a quick mental check is good sometimes. And anyway, I used a calculator on this one, and I got approximately 63.75 out of that one. And so the idea here is the area was more above than below, which is why it's positive. So more area above x-axis than below. All right. How's that feel? Seems okay? All right. So before we do our quiz, I just want to summarize what we had just done, because the way I try to teach this stuff is exploring it a little bit, like thinking about how are we going to add up the area, you know, I talk about doing the plus C and then we take it away with the other thing. And so sometimes people are confused at this point is what I'm trying to say. And so I'm trying to just lay out the two things we've talked about. We've talked about indefinite integrals, right? That's the first thing. That's when there's no bounds, right? This is the difference, is when there's a bounds on the integral versus no bounds. If there's no bounds, like the first one, it means just do the antiderivative. And since we're just doing the antiderivative, we do plus C to account for constants. So this is just what I would describe as finding the family of antiderivatives. And as a reminder, by the way, this is nothing new, but this is a nice page to have good notes for, because when you're studying for the test, which is in 2 weeks from today, this might be a good page to just get your mind straight about the differences, right? So anyway, finding the family of antiderivatives, we have the plus C part on the end. And what we're doing here is we're representing all possible antiderivatives of little f of x. Right, let's do a quick example of this. For example, if we integrated 1 over x, remember that's one of the ones with a special rule, it becomes natural log. And we should know that because when we take the derivative of natural log, we get 1 over x, right? So we're doing the opposite there. And the idea is the plus C means it could be any number of possible answers. So if I kind of zoom in on this a little bit here, if C was 0, it would look like just natural log, right? That's ln plus 0. If ln, or if the C was 5 or something, it would move it up. Maybe that's ln plus 5. We don't know. If it was negative, it would move it down. Maybe it's this one. And so we don't know which one it is. It could be any of those possibilities. And we're going to talk about how we know which one of those it is in just a second, but just sort of setting up the indefinite integrals. What's about what I'm trying to say there, though? Where we clarify that with the definite integral part. So the definite one is the one we just looked at. That's the one that has A's and B's in it, right? That's the one that you get a number out of. And we get a number out of there because it finds the area bounded between little function f of x and the x-axis. That's what we just did today. And I should be clear, from A to B. Right, like people are having questions like, oh, well, why isn't this part of the graph shaded versus another? A and B tell us sort of what part of the graphs we're doing, right? And so let's integrate 1 over x again. But let's put bounds on it, right? So we just integrated 1 over x just 1 second ago, and we got natural log plus c. If we integrate it with bounds, what does that mean? All right, so let's go from 0, or not 0, because it's 1 over x, 1 to 100 of 1 over x. All right, what's that going to do? Well, we still get natural log, but we plug numbers into it. Right, and when you plug numbers in, we get numbers out. And so when we actually plug numbers in, like ln 100 minus ln 1, we get a number out. And so what is that? Well, that's some area we just calculated. And so pictorially, graphically, we just found this area. This is what 1 over x looks like. We went from 1 to 100. So we started somewhere right there and we went way out to 100 and we found this area. Okay, so I would strongly encourage you to write all this stuff down, even if it makes sense right now, right? Because in 2 weeks, we want it to make sense when you're studying. When the final comes around, you want this to make sense. And I hope this can be a clarifying page for you. This is what 1 over x looks like, by the way. Okay, that's about what I'm trying to say there.
I'd like to ask a question.
Yeah, go ahead.
Why is 1 over x? Why can't we make it use an exponent?
Yeah, good question there. We had talked about that. If you try to do 1 over x, and if you try to write it as x to the minus 1, when you add 1 to that and divide, you divide by 0. And so that's no good, which is specifically why we instead have the rule that it turns into natural log.
Okay.
Other questions? All right. So the last thing I just want to touch on here is how do we actually get the plus c? Because the thing I just sort of mentioned, and this is leading into another interesting topic that has lots of implications, but when you integrate 1 over x, you get ln plus c. How do we know which one of those graphs it is, right? Just circled them in yellow. Could be any one of those things. Well, in order to find out what the plus c is, we need more information about the function. Maybe I should actually hold off on this till next time. Let me see how we're doing on time. This might take me 10 minutes. How long
Wouldn't
is
the
this
plus
quiz?
c be the y-intercept?
So if it was, so the question online was, isn't the plus c the y-intercept? It's the y-intercept in a linear function, but in a natural log function, that just shifts the thing up and down. I think I'm gonna hold off. Oh, gosh, I feel like I have like just enough time. I don't really want to push it. All right, I am gonna do this. I think we can do this. So how do we find the plus c? Let's do a simple example. Let's say we integrated 2x. Super easy to integrate, right? Anti-power rule. 2x squared over 2 plus c, which is just x squared plus c. All right, and so to the point we're trying to make here, how do we know which one of these graphs is it? Is it this one? If c is 0, it would be this one. If c were 10, it might be this one right here. If c were negative, it would be down here, right? Maybe this is like x squared minus 5. And so the way we actually figure out which one of those, do people see what I'm saying there when I try to draw these different graphs? We don't know what c is, and maybe I'm taking this for granted. C just moves the graph up or down, right? You're just adding something to the y values. For folks who are in my pre-calc classes, right? That's just an up or down vertical translation. And so that's why I'm writing like these graphs that are going up and down, depending on what c is. Sorry if that wasn't clear before. And so the way we're figuring out which one that is we know something about the graph. So let's say, suppose we know anything. I'm just going to make something up. F of 5 is 20. If we know f of 5 is 20, that means when we plug in 5, we should get 20 out. And so we can plug 5 into the function, set it equal to 20, and figure out what c is. Right? That's how this works. That means that when I plug 5 in plus c, I should get 20 out. Right? That's what f of 5 equaling 20 means. And now the only thing that's missing there is c. And so we can figure out c, right? 25 plus c is 20. That means c is negative 5. Oh, so the graph is actually that lower one where c is negative 5. Right, so the sort of the takeaway here is if we wanted to integrate 2x dx and we knew f of 5 is 20, then the answer ends up being x squared minus 5 is our integral. That's our capital F. Right, so this is what's known as an initial value problem, where we need to know something about the function we're integrating, and then it lets us figure out what the plus c is. And this is what people do who are studying COVID, for example, or in my research, I do like math modeling. I don't know if anyone's ever seen me talk about that, but what you do in these math modeling things is you write down a different differential equation, like the one in the next example, for example. It tells us how things are changing, like COVID cases, for example. We solve the differential equation, it gets a plus c, but then we know something about COVID cases. Like we know, we go to Fitchburg Public Health and they say, well, on this day, there were this many cases. And so then you use that information to get the plus c. And so this is what I would call an introduction to like differential equations and what's known as an initial value problem. Questions about that idea? We're going to look at this other example here. I was going to let you try it maybe. I think we've got enough time for that. Thoughts about how this works though? So in this example, P prime is telling us how a population's changing, right? And it's telling us, well, we know that at t equals 0, there were 300 individuals. That means P of 0 equals 300. So everyone see how that translates into that? So we're given P prime, but we know something about P, right? And so we're going to integrate this thing. Where we know P of 0 is 300. Right, this is the problem setup. Is that okay? What happens when we integrate E? Nothing, right? And so this doesn't actually change. And maybe the other way to think about it is the 150 is just a constant coefficient, right? And so you don't do that, you don't do anything with it. You just bring it out in front. And so this just stays the same and we get plus C. But we know that when we plug in 0, we should get 300. And so that lets us find out C. Right, so I know that when I plug in 0, I should get 300 out. E to the 0 just goes away. C is 150. And so we started out with the derivative, but then we got the actual function. I think it's really important to kind of write that down. Let me sort of summarize what we just did. We had P prime. And we knew something about the function, and then we ended up getting the actual P. And that's super valuable because if we wanted to know what the population is down the road, that's usually what we care about. What's going to happen in 5 days from now? Like, what's the population going to be in a year? The thing that we solved tells us that information. We started out with something that tells us how it's changing, but we use that to figure out what's going to happen however many years down the line we care about. Right? You plug in something for T now, and we can figure out the future population. All right, I'm going to end it right there. Questions for anyone? You guys still awake out there? Just kidding, but questions? All righty. Let's do this quiz. I'm gonna pass it out. Still willing to answer questions. Going once, going twice. Oh. So once folks online are all set with their cameras on, I'll send it out there. I'm gonna, yeah. Yep. So the question is like, why did the 150 move out front, right? So that has to do with the constant coefficient rule. Where does it say that? Right here. Well, if you're trying to integrate something that has a constant multiplying it, you just pull the constant out front and just integrate the thing with the x in it, right? Like this kind of idea. If you had integrating 2x, you don't really care about the 2 so much. You just think about what's going on with the x. So that's what was going on with that 150, right? The 150 was just a constant multiple that is not, doesn't have a t, right? There's no t with the 150, and so it doesn't really come into play. Yeah, thanks for that question. Other thoughts? All right, great. All right, it's coming through the chat right now, remote folks.